guess they don't take attendance anymore or something.
Okay, guys. In lab section on Blackboard, I have 4 videos, okay, from previous semesters. First video is kind of an introduction to this idea of what ANOVA is and analysis of variances. The second one is a demonstration using Excel to actually work it out by hand, manually calculate sum of squares and divide by the degrees of freedom and so on and so forth. Everything that's in that little chart that comes out of SPSS to do that manually. The third one is doing the same problem, the same data using SPSS. And the fourth one is running the post hoc tests using SPSS. So those videos are already on there. I'm gonna just kind of introduce it, like rather than play the videos. You can always go home and play them. And I'm also recording this session as well. But I just want to describe to you like what this deal is all about. What we're doing here. I think you probably got a good idea from the lecture, but I want to make sure that it makes some sense to you. We're connected. Okay. Okay. So the deal here is that we are comparing 3 populations by taking samples from each one of the 3 populations. And we're interested in demonstrating whether or not there's a difference between the means of these 3 populations, or whether they're so close together that we really can't tell that there's a difference. Whether they're really the same population or the same, or they share basically the same distribution. Okay. So what we're doing is we're comparing means, but we're doing it by examining the variability of the data that we're working with. Okay, so really what we're doing, we're really not looking at the numbers themselves as much as where the numbers are and how much they're spread out. Okay, so I'm going to give you kind of an analogy, the same analogy that I used in one of those videos. Okay, so now imagine that you have 3 trees, right? So you got 3 trees. Oops. There's a trunk of one tree. There's a trunk of a second tree. There's a trunk of a third tree. And these 3 trees have a bunch of leaves on them. Okay. There's 2 ways. So a lot of times when you look at a tree from a distance, and there's actually more than 1 tree, like say 2 trees, when you look at them from a distance, if they're very close together, the trunks are very close together, you can't distinguish them as 2 trees. They look like basically 1 tree. The leaves on the trees, basically, a lot of times on trees, the leaves are basically, you have a pile of them like that, and then the trunk is coming out of the middle. That's a lot like our normal distribution, right? So if you have 3 trees and they're close together, it's hard to distinguish between them, right? Well, if you really want to distinguish between them, there's a couple of things that you can do to help yourself tell them apart. Okay, one is, especially if say you wanted to be able to, if you wanted to be able to plant them and be able to look from a distance, see there's really 3 trees there. Okay, one of the things that you can do is you can make sure that let me get rid of this. You can make sure that the trunks of the trees are far apart. Okay. trunk of this tree, trunk of this tree, trunk of this tree, and you can have a fairly big group of leaves up there. But it's pretty easy to tell them apart because the middle of the tree is distant from middle of the trees are distant from one another, right? Imagine now that that trunk is the mean of each one of these trees, each one of these groups of leaves, right? So one thing that'll help us distinguish them or demonstrate that there are three different trees and not one tree is that the means, the middle of the tree, are far apart. The other thing that'll help us do this and which will mean also that the trees don't really have to be that far apart, is if the trees are not as wide, if the leaves aren't as spread out. So, for instance, if you have trees, ideally that we'd have the trunks are far apart, and the leaves are, it's a kind of a vertical tree where the leaves don't spread out very much. Then it's really easy to tell that there's three trees there. Now, when we talk about data, what we're saying here basically is that we want the means to be far apart, and we want the variability between the means, the differences between the means, to be far apart, and we want the variability within each individual trees, the leaves of each individual trees. We don't want them very variable. We want them packed together closely. This makes it easy for us to distinguish these. Okay, so if you wanted to create like a factor from start, what you would do is you would say, I'm going to create a statistic called an analysis of variance, ANOVA, and I'm going to call that F. And I'm going to say that on the top of that, I'm going to say that I'm going to put the variability between the means, between the groups or between the means on top. And I'm going to put the variability within the groups on the bottom. Okay, I'm going to create a fraction that does that. Well, what is this? The variability between the means. That's the distance between the means. In order to get a bigger F score, in order for F to be larger, the top of this needs to be big, and the bottom of this needs to be smaller. We want this to be bigger and this to be smaller to get a bigger number, right? Simple fraction, right? So, in other words, that's exactly what we want. We want the distance between the means to be large, and the distance within the groups, the variability within the groups, to be small. The smaller it is within the groups, and the larger it is between the groups, the bigger that this F value is. Once we calculate what that F value is, then we can create a table for it, where just like our chi-square, where the bigger the number is, the less likely it is that these different means have the same value. So we want a big F score that we can compare to a critical value of F that's based on the sample sizes, in other words, degrees of freedom, to be able to reject our null hypothesis. Most of the time, you're not going to be doing this by hand. There's a demonstration of it that you can play that I do by hand on one of those videos. But most of the time, you're going to be using SPSS or R or SAS or something like that to do these calculations. So what is that based on? How do we create that factor? Okay, and the reason why I'm doing this is because these numbers are going to wind up in our SPSS table, and this will help you understand what those numbers are. Okay, so I want to calculate this F factor, right? This analysis of variance. So on the top, I want the variability between the means. Right? Bottom, I want the variability, a measure of how variable these things are within the groups. Okay, so sometimes they call those two things together the total variability, but we really in ANOVA we split them up. Okay, so how can we measure variability between the means and within the groups? Well, I'm going to go back to something we learned initially, and that is sum of squares. Okay, so when we took the sum of squares, what we did was we took the average value for the means, right, for instance, and we looked at the difference between each mean and the average values for all of the means, for all of the entire samples. So we're going to take that, square those numbers, just like we did when we calculated variance and standard deviation. Square those numbers and put them together, add them up and put them up here as the sum of squares. The only problem is that when we do that, right, that creates a very large number, because when we go to the bottom, especially, we're going to be dealing with a lot of individual values in the samples. We're going to take that, but we're going to divide by the degrees of freedom. So for the top part of this is going to be the variability between the sum of the squares of the differences between the means divided by the degrees of freedom. Okay, what do you think it might be for this, for 3 means? Take a wild guess. 2, right? Okay, n minus 1, 2, right? We're going to call that the mean sum of squares. Right? And what is that really? Isn't that almost like what we calculated when we called it the variance? Right? We took the sum of squares divided by the degrees of freedom. We just call it the variance when we're working with a regular sample. We're going to do the same thing on the bottom, except we're going to take the sum of squares of the differences for each individual group in each individual and with each individual mean. We're going to take for each one of those 3 groups, we're going to find the mean, find the differences for each value, square it, and then add up all the values for all 3 groups, and then divide by the degrees of freedom. Right? So this is going to be like for instance, if we have 20 people in each group, it's going to be 60 people, 60 squares. Sum of squares is going to be a sum of 60 values, and then we're going to divide by the degrees of freedom. This time the degrees of freedom is going to be 60 minus the number of groups that we have, 60 minus 2. Okay, so it's going to be 58. So we're going to call that degrees of freedom 58. And we're going to take these 2 numbers and get a number from it. Say it winds up being 5.2 or something like that. Then our task is to determine whether or not that's a big enough number. In other words, if the means are far enough apart on top, and if they're if they're far enough on top, and if they're narrow enough on the bottom, small sum squares, in order for us to say that we have less than alpha, we have less than a 5% chance. Alpha is less than 0.05, less than a 5% chance if we're wrong, if we reject the null hypothesis. So now that we've gone through all this, we should go back to what we should have said in the beginning. What's our null hypothesis? The null hypothesis is that all these means are the same, right? So in other words, we have a sample, X bar for group 1, X bar for group 2, X bar for group 3. They really represent the means for the populations, what we're really interested in. So our null hypothesis is mu1 is equal to mu2 is equal to mu3, and our alternative hypothesis, in this case, our alternative hypothesis is that any 2 of them are different, okay? Because it could be that this is much different than these other 2, or all 3 of them could be very different, and so on. We don't know yet at this stage. So this is our null hypothesis. Our alternative hypothesis is that at least 2 of the means of these populations are different, or different enough for us to reject the null hypothesis with less than 5% chance of being wrong. Okay, so let's give this a try in SPSS. So I'm gonna, again, unless we have more time, I'm not gonna bother doing this with Excel. But you can see it done with Excel if you want. Well, by the way, just so you know, in the video, the trees that I used, I took pictures. The trees I took pictures of and used there were at the Brooklyn Botanical Gardens. They have an enormous grove. They literally have a grove. They have like this football field sized area where they have lines of 2 double lines of cherry trees, and then another area around a giant koi pond that they have there. That's absolutely spectacular. And if you go to, I'm going to Google this for you. If you Google Brooklyn Botanical Gardens and the cherry trees, they actually have cherry blossom. The first link that comes up is cherry blossoms at Brooklyn Botanical Garden. They have a map that shows you whether they're in bloom or not. They update every day. right? So if you went right now, all of the ones around the pond are in bloom, but these two really spectacular, this spectacular field of them is not in bloom yet. It's a little cold, so it's a little later than usual. They have a festival at the end of April. They may not be in bloom for the festival, but you should keep an eye on it, because it's a great time to go down there and take a look at this. It's really spectacular. Here, get a little video here. No, there's no cherry blossoms on the exam. Was that what you're going to ask? You don't worry about Excel. For the exam, you're not going to use Excel to do these calculations. But there's a demonstration on there so you can see how the calculation actually occurs. Okay, so I'm not going to go ahead and do that now, though. Okay, so let's take a look. Let's get away from the Brooklyn Botanical Gardens. And let me get a look at, here's one set of data. This is the set of data, a simple set of data that I used for the demo that's on Blackboard. And these numbers don't mean anything, actually. It's just 3 groups of numbers, 5 values each. If you want, they're on Blackboard now, so if you want to download them, I think the name of the file is, as soon as it comes up, I'll tell you, SPSS demo for ANOVA.sav. Okay, and for want of any better thing to call it, I call it 3 groups. I call one group Fred, one group Jim, and one group Alice. And each of them have 5 values. Maybe there's some sort of scores or something like that, or biological markers or something like that, but they have 5 values. Okay, so now what I'm interested in is knowing whether there's a difference between the means of these 3 groups. So one of the things I might want to look at to start off with, just in general, for instance, if you're working on a project, I might be interested in looking at the descriptive statistics first. In other words, what's the mean, standard deviation, variance for these 3 groups, for these 3 samples? Analyze descriptive statistics. Since I'm going to split it up into 3 groups, in other words, I want to parse it or factor it into the 3 groups, Fred, Alice, and Jim, I need to go to Explore rather than frequencies and descriptives. So I go to Explore. Into the dependence list, I moved a numerical variable. Notice something here? It thinks both of these are categorical variables. And the reason why it does that is because the numbers I used were 1, 2, 3, 1, 4, 6, 7 for the numerical variable. And it assumed that if the numbers are whole numbers and that small, that they'll probably stand for something. So it incorrectly assumed that they were categorical variables. I'm going to go into the variable view, and I'm going to go to measurement, which is the variable name, and I'm going to change that from nominal to scalar. So now it knows that those are numbers and not just something that represents another categorical variable. So I'm going to go back to data view. I'll try this again. Analyze, descriptive statistics, explore. And I only did that because there's a chance that SPSS may misinterpret the data. So I want to make sure it understands that measurement, you notice there's a ruler there now, is a numerical variable. We're going to calculate means. I'm going to move that into the dependence list. And then I want to break it up into the groups, which are Jim, Fred, Alice. I'm going to put that into the factor list. Okay, if I want, I can click onto statistics, and it's already going to find almost all of the descriptive statistics we're interested in, including 95% confidence intervals and so on. So I'm not going to bother with, why not? Let's do a plot. Well, no, it's automatically going to do a box plot. I don't think a histogram for the 5 values is going to tell us much, so I won't bother with it. I'm going to click OK, and it's going to go ahead and do our analysis. Okay, so what do we wind up with here? Let's take a look. Okay, we have 5, total number of values in each group is 5. They're all valued, there's no missing values, and so on and so forth. But individually, the mean for Fred is 1.8, and our standard deviation is 0.87. The mean for Jim is 3.4, and the mean for Alice is 4.4. So 4.4, 3.4, and the first one was 1.8. So I'm already starting to think, gee, maybe I can demonstrate a difference between at least the one with the highest mean, the one with the lowest mean, or maybe all three of them. Maybe I have enough data here and the variability is such I can demonstrate there's a difference between all three. So our null hypothesis, the mean for Fred is equal to the mean for Alice is equal to the mean for Jen. Right? Alternative hypothesis is that they're all different. Presumably, now I don't know what it is for this small number of this very small sample set, the standard deviations, the variability should be approximately equal for these three, right? I'm going to look at it, but I'm going to do it anyway, even if they aren't. Okay, and it's about 0.87, about 1.14, and about 2 point, quite a bit different. There's a bit of a difference with that third one, but I'm going to go ahead with our analysis anyway. Okay, the other thing that we've gotten here is we've gotten a confidence interval, I believe, right? So our confidence interval for, where is it here? Our 95% confidence interval for Fred is 0.76 to 2.84. For Jim is 1.98 to 4.82, right? They overlap a bit. And for Alice is 1.83 to 6.97. Well, look, that looks a bit different than Fred. It looks like it doesn't overlap, Fred, there. So I'm a little encouraged there, right? Because at least one of them, the confidence intervals don't overlap. So I'm going to go ahead and do my analysis of variance. Analyze. Now, what am I doing now when I do analysis of variance? I talked about nothing but variability here so far, right? All the numbers I worked with were variability, but I'm comparing means. So analysis of variance is buried in comparing means, compare means. And we're going to do one-way analysis of variance. Don't worry about the one-way part. Okay, dependent is going to be what we're going to find the mean of. That's our measurement. And the factor is going to be, the groups are going to be enough go into our factor. Notice it doesn't, remember in when we did the t-test, it asked me to tell it what the numbers that represented the group were. That's because, for instance, if you were looking to do a comparison between two means of two ethnicities, but the ethnicity variable had more than two values, and you wanted to just compare African Americans to Hispanics, you could tell it just do the t-test for the value 2 and the value 7, right? So there were many values. So you could pick out which two you wanted to do. In this case, analysis of variance is going to, I'm sorry, t-test, right? In other words, in the t-test, it came up and asked us, as soon as we move something into the factored box, it came up with two question marks and wanted to know which two groups. So even if it only had two groups there, you still had to put in 1 and 2 or 0 and 1. With this, it doesn't ask you because it's going to compare all the means within that group, right? That's what analysis of variance does. That's why it didn't pop up there. Okay, so I'm not going to bother with post hoc tests right now. First, I'm going to run our analysis of variance. Click OK, go back to the output table, and we wind up with this table. Okay, let me get this up a little bit further so we can see it in the back. So let's take a look at what we have here. Okay, so the sum of squares between the groups, that's the sum of squares of the means, right? The three means, we found the sum of squares of these squares and the difference of the means, add them all squared, add them all together, is 17.2. The degrees of freedom is 2. And if we take 17.2 divided by 2, we get the mean sum of squares, which is 8.6. That's where that number came from. What about the sum of squares within the groups? Well, there's a lot more values within the groups. So we took each group, found the mean, found the difference between each value and the mean for that group, squared it, added them all together, and we got that number, right? Now, there are three groups. There's 15 numbers. Actually, I was wrong before it's split. Subtract 3. Take 15, subtract 3 for the number of groups, and the degrees of freedom is 12. Take 25.2, which is the sum of squares within the groups, divide by the degrees of freedom, and we have the mean sum of squares within the groups themselves. We want this number to be small and this number to be big, right? In other words, we want the means far apart, and we want the variability within each group to be very narrow. We want these numbers to be this number to be small. So now our F statistic is the mean sum of squares for between the means and divided by the mean sum of squares within the groups. So 8.6 over 2.1 is equal to 4.095. Now, if we were doing this manually, we'd have to go to a table. In fact, I think I might have one. Just so you can see it's there. Whoop. At this stage, we'd have to go to a table. And let me see if I can't find it. I think that's it. Nope. Well, that's the analysis of it, the distribution for the analysis of variance. That's a bid. I don't know why that came up now. Good. Let's get rid of that. Okay, so here's our table for analysis of variance. Looks a lot like a chi-square distribution, doesn't it? The idea here is the bigger that F-score is, the less likely we would get that outcome if there's no difference between the means. Meaning the less likely that we would get that outcome if we reject the null hypothesis. So we want this tail to be less than 0.05. We want to be far enough over that's less than 0.05. Well, in this case, though, we got a problem. We have 2 degrees of freedom. We have degrees of freedom for between the means, and we have degrees of freedom for within the groups. Anybody remember how many degrees of freedom between the means we had? It was 2, right? How many degrees of freedom we had within the groups? It was 12, 15 minus the 3 groups, right? So now we got to figure out which of these is which, because here's degrees of freedom here for a probability of 0.05. Here's degrees of freedom here, and usually what you can do is if you look at this column here, that's a very big number. So that's going to be the degrees of freedom within the groups, which is going to be a lot of values. And across the top is the degrees of freedom between the means, right? So we're looking for 2 degrees of freedom between the groups and 12 degrees of freedom within the groups, right? Which brings us to this number 3.89. That's our critical value of an analysis of variance. That's the value we have to exceed in order to have less than a 5% chance of being wrong if we reject the null hypothesis. In other words, we'd only get a value that big, wherever it went, 12 and 3.89. We'd only get a value that big if we would only get that value 5% of the time when there was no difference. So if we get a value bigger than that, it's less than 5% of the time we'd get that big a difference when there's no difference between the means. So what did we get? Anybody remember? It was 4 point something, right? So in this case, what will we do? Reject the null hypothesis, right? Because there's less than 5% chance that we're wrong because we've exceeded the critical value that we need to exceed. Everybody okay with that? Okay, let's see if SPSS gave us the same result. SPSS, on the other hand, has all these tables built into it. So instead of like comparing this to a critical value, it's actually going to calculate the p-value. That means the probability you'd be wrong if you rejected the null hypothesis. And the p-value of significance is 0.044, right? In other words, there's a 4.4% chance you'd be wrong if you reject the null hypothesis. Our threshold for that is that we're willing to risk 5% chance of being wrong. So since it's less than an alpha, 5%, we can reject the null hypothesis. The same result as we got when we compared those values. Great. Now we know we can reject the null hypothesis. But the null hypothesis was that all of these means are the same, right? So what we said is that they're not the same. But we haven't discovered which ones are different at this stage, right? So in order to do that, we do a post hoc test. Post hoc in Latin, I took a little million years ago. Post hoc in Latin, I think, means after the fact, basically, right? Post and hoc means theory or fact or something like that. So after the fact, we successfully rejected a null hypothesis. We can go back and do another analysis. So now I'm going to go to analyze. Again, we're still doing the same thing, compare means, one-way analysis of variance. And I'm going to go in here, and now I'm going to go click on the button that says post hoc. I'm going to choose one of these tests. Now, each one of these tests has uses a different strategy for determining if there's a significant difference between the means. And if you went, I believe if you go into SPSS and into the help section, or better yet, if you Google the test online, you could probably find information about what's different about what's unique about that particular test, which ones are more conservative, which ones are less conservative, what particular situation one might be better than another in. Be honest with you, every once in a while I bother to try and look some of that stuff up. Usually the tests we use most frequently are least squares, LSD, Bonferroni, or Tukey. We usually stay away from the others. If you ask me now, I haven't looked at it in at least a year, so I don't remember what the difference is anymore. I believe Tukey is the most conservative, right? Bonferroni is a fairly conservative version of it also. One of them is just basically dividing the alpha, in other words, requiring it to have a p-score of less than 1/3 of 0.05. So it's really pretty conservative. So one of these is most conservative. Professor Weicker suggested that we stick with Tukey, so that's what I'm going to stick with for tonight. Okay, so that's going to test now individual comparisons between each of the means without the danger of increasing our probability of being wrong. Remember, the reason why we're doing all this is because if we tried to just do a t-test between group A and group B, and then between group A and group C, and then between group A and group C, if we did 3 t-tests, and each one of them came out to be 4%, for instance, right? We might reject the null hypothesis, but we'd be multiplying our error. It's kind of like Russian roulette, right? If you keep doing it often enough, you're bound to be wrong, right? So I'm going to say Tukey. I'm going to say continue, and I'm going to say OK. Now, SPSS does something that's kind of weird, but you'll see it does this a lot for whatever reason. What it does is it says, okay, I'm going to compare the analysis of variance for Fred versus Jim, right? I'm going to take Fred, and I'm going to compare it to the other two groups. And then I'm going to take Jim and compare it to the other two groups, right? But the thing is because it repeats that analysis for each one of them, it actually does the analysis twice for every possible combination of those groups. So if you go across here, let's see, here's our significance. Here's our probability of being wrong if we reject the null hypothesis that there's a difference between those two means, right? So that any of these, we have any winners here? Well, look at this. The significance for the difference between the mean for Fred and Alice is less than 0.05, is 0.037, right? But notice they do the same test down here. They compared Fred and Alice, and then they compared Alice and Fred, but they got the same result, right? It's just a peculiarity of how it does these tests. A few of the tests are like that, right? So can we reject the null hypothesis that Fred and Jim are different? No, not less than 0.05. How about Fred and Alice? Well, yes. And how about Jim and Fred? Well, Jim and Fred, not so much, right? It's also 0.229, right? So we only have one pair of means that we can say with 95% certainty, with less than 5% chance of being wrong, that the means are different. And that would be for Fred and Alice, right? And that makes sense because those are the ones that were furthest apart. Those are the ones that the 95% confidence intervals didn't overlap, and so on. Now, you don't want to use the confidence interval, so it's not a dependable source, but it kind of can be something that you can just check for yourself. Okay, so there's other data on here, so maybe you guys repeat this analysis, and then we'll do it together. Hang on a second, let me find a good one. Okay, I'm looking at fan motors there. That's not what I want. Let's see, I think IQ data. Let's try that.
So, is the outcome always a numerical value?
Yes. Right, it's always going to be a significance, a p-value. Oh, you mean for...
No. Or it's always a numerical variable.
F. For F, you mean?
To use ANOVA.
Oh, to use this test? Yes. It's always because you're comparing means.
The outcome is always numerical.
Yes, because you're comparing means. This is
Right, this is a means.
Exactly. So it's always something that you use on a numerical variable. right? It's not like chi-square is categorical, odds ratio is categorical, right? So this is not for two categorical variables. The only categorical variable here is the groups, right? Yeah, exactly. Okay, so let's see what we got here. We got physics, math, and chemistry students, and we're comparing their, well, I said IQ here, but obviously it's not IQ, it must be a test score or something like that. So why don't you guys open that data set, IQ data .sav, open it in SPSS, run your analysis of variance, and if your value, your p-value, is less than 0.05, go ahead and run it in one of your post hoc tests. In the meantime, I'm going to open up that original one. I'm going to run Bonferroni, Tukey, and LSD and see if there's any difference between them, just as an academic exercise.
So it's compare means, one way ANOVA?
Compare means, one way ANOVA, right, exactly. If you wanted to, and you wanted to explore a little bit more, you could say descriptive statistics explore, just so you can get all that other data about your population, right? What are the things you're going to do when you do your project? Is in addition to doing whatever statistical test you wind up doing, you're going to want to describe the population. You know, what are the variables you're working with? If they're numerical, what's the mean for the population? How variable are these values? What's the range? What's the interquartile range? Maybe you can chart a history. Maybe you want to create a histogram to demonstrate that it's normally distributed. Maybe you want to create box plots so you can see how whether the mean is in the middle and whether the data is skewed or not. You know, so keep in mind that when you actually do the project, you're going to want to do some of these descriptive statistics as well to just be able to describe your data. Okay, so I'm going to, let's see, where did it go? So I got it still got it open. Oh, no, I got to reopen it. Okay. It's iqdata.sav. Should be in the lab section under the lab in SPSS. It's under those, most likely buried under those videos. Okay, just right click on that, save it to your desktop, and double click on it on your desktop. It should open. Analyze, compare means, variance, group. Did it again. I didn't save the file after I made the change in the variable type. Let me say save. Oops. Okay, Tukey, we already showed the results there. 37. LSD 0.015.015. So this made it look like more of a sure thing than we had before. So that's a less conservative test. In other words, you'd be more likely to be wrong if you use that test because it exaggerated the difference between the likelihood to be wrong. This is a more conservative test because it was almost just barely came in under the wire. So Bonferroni looks like a more conservative test based on this. Right? So it's only 0.05 or 0.045 versus 0.037. And so this could have easily been over 0.05, leading us to maybe think maybe we need a bigger sample or something like that to be able to demonstrate this difference. But they all agree in terms of the only pairs of means that can reject that you can reject a null hypothesis for. So they came up with different answers, right? So there obviously is some different mechanism going on behind there in terms of how it calculates these probabilities. my memory were better, I might be able to, give you a little bit better information on how it does, what it does. But I do remember Bonferroni being probably one of the most, Bonferroni being the most conservative. I'll give you guys a few minutes to work on that other one. If it doesn't, if you don't get a p-value less than 0.05 when you do the initial analysis of variance, give me a heads up, okay? Because then clearly you wouldn't bother running the post hoc test unless you pass that hurdle first, right? We know that that's obvious, right? In other words, if you can't say with 95% certainty that you can reject the null hypothesis, that there's a difference between at least one of those, two of those means, then you don't want to run the post hoc test just for the hell of it, hoping you'll get lucky. It's kind of cheating. Beautiful, isn't it? Okay, maybe we'll run it together now. Okay, so I'm going to go in here. I'm going to say analyze. I want to compare the means of these three groups. Let me do the descriptive statistics first. Analyze, descriptive statistics, explore. I'm going to move our numerical variable, which is the IQ score. So I guess it must be actually a test or something like that, or some oddball IQ score. I'm going to move the grouping variable into my factor list. And I'm going to click OK. And it'll come up with all these interesting statistics for us. Here's our box plot, right? Not the variability in these is a little bit sloppy, right? But not exactly the same. This one really is not much variability. Anybody remember what the word for that was? where we want the variability to be the same within the groups. Homoscedasticity. Yeah, homoscedasticity, right, exactly. Exactly. Yeah. When you're lucky, you get that. Most of the time, it's hard to find. So, may have to compromise a little bit there. Okay, here's the means 35.8, 35.88, and 48.2. Okay. I made the chemistry students smarter because I was a chemistry student. So what the hell? I love that banter on Big Bang Theory about between the engineers and the physicists and stuff like that. There's a lot of that goes on, let me tell you. So at any rate, I'm going to go ahead and do the analysis of variance to see if I can tell that there's a difference in the mean. I can already see that it's going to be tough to demonstrate a difference in the mean between math students and physics students because the means are so close together already. So I'm going to say analyze, compare means, one-way analysis of variance. I'm going to move our numerical variable measurement into the dependence list and move our grouping variable into the factor list. I'm going to say, okay, I'm not going to run post hoc tests yet, at least not intentionally. And sure enough, look at this. Let's see. Now, keep in mind here, see this table here? If I covered up any one of these boxes, you should be able to fill in that number for me now, right? Because you know that this value here is just this value divided by this value, gives you that value. And this value here is just this value divided by this value. And this value is just this value divided by this value, right? So I could cover this up, or I could cover this up, or I could cover this up. If I cover any one of those boxes up, you should be able to recreate that, right? Because they're all interdependent. You know where they come from now. You know why they're there. Okay, that's why I like doing this, rather than just showing you what drop menus to use. If you know what you're looking for, it makes it a lot less likely that you're going to make an error or use it incorrectly. Okay, so in this case, the significance, the p-value is well under 0.05, right? Our f-value is 20, the p-value is well under 0.05, so we can go ahead and run our post hoc test. So I'm going to go to Analyze, Compare Means, One-Way Analysis of Variance. I'm going to go into post hoc, and I'm going to pick Tukey, and I'm going to click Continue. I'm going to say OK. So our post hoc tests will come up, and again, it'll duplicate them. But I can see that that there's a couple of things that we see here. That there's a significant difference between the score for physics students and chemistry students, and the score between math students and chemistry students. Right? So now we have two means that are different. In other words, chemistry students are different, significantly different. The means for chemistry students are significantly different than for physics majors, and also significantly different from math majors. Well, how about physics students and chemistry? How about physics and math students? Well, physics and math students, well, that's not significant. So we can't say that those means are different. Okay? Okay, good. Now, what I'm going to do now is I'm going to pull open a kind of a data set that has a lot of different variables in it. And I'm going to pick out stuff at random. And I'm going to ask you what test I should run on it. How's that? I'm going to take this NC birth 800 mod.sav. It's a mouthful. Again, 800 or 700. Some of these files have seven. They're not all the same. Some of them have 799. Some of them have 800. I think we've monkeyed with them every once in a while. And I'm going to open that data file up. I'm going to look at the variables first. I'm going to go to Variable View. And here are my various variables and so on and so forth. In here, for instance, I have the mother's age. That's a numerical variable, right? Scalar. Another scalar variable I have is the amount of weight that the mother gained during pregnancy. Another numerical variable is the weight of the infant at birth in ounces and in kilograms or milligrams or grams. Not milligrams, grams. Right? So I have a lot of numerical variables here. How about categorical variables? I have whether the mother smoked or not, right? That's two values. I have whether the mother is Hispanic or not. I have the race of the mother. What do I have in there? I have 8 different values for the race of the mother. Okay, that's interesting. How about, I saw another one that was kind of like that, called ethnicity or something like that. So where is that? Ethnicity of the mother. And if in that one, I have 4 groups: non-Hispanic, white; non-Hispanic, black; Hispanic, and other. Okay, so I got 4 groups there, right? Let's say I wanted to know if there's a difference in the birth weight for babies for these 4 groups. Non-Hispanic white, non-Hispanic black, Hispanic, 4 groups. I want to know if there's a difference in the birth weight. The birth weight's a numerical variable, so I'm comparing means. I'm saying U for this group is equal to U for this group is equal to U for this group is equal to U for this group. What test do I run now? Analysis of variance, right? We just learned that. So let's go ahead and run that. Analyze, compare means, analysis of variance, one-way ANOVA. I'm going to move into there. I'm going to move the weight of the infant. I'm going to choose ounces because I'm old and I'm resisting the changeover to the metric system. And I'm going to choose, actually, my background is chemistry and engineering and stuff like that. And in the 70s, they were determined that we were all going to switch over to the metric system. And they were putting up signs, road signs and stuff, but there was such resistance to it that they just simply gave up. So we're still stuck with the English system, or standard system as they call it, right? And into the factors, I'm going to put the ethnicity of the mother, which has 4 groups. I'm going to say, okay, I'm going to go ahead and run this. Okay, so let's see how our analysis of variance. Remember, we have 4 groups now. Remember that table we had? 3. We had 3 groups, 2 degrees of freedom. We had 15 people in it, which was 12 degrees of freedom because of 3 groups, and we found the F value that we needed. Well, now we have 4 groups, and we have 800 people in it. Less 4 groups, that's 796 degrees of freedom, right? We'll see if that actually comes up there, right? So it's a much bigger F score that we're going to have to exceed. So let's see what the F score is here. The F score here is 8.222, right? Let's see what we have here. That's the sum of squares between the groups. Divided by 3 degrees of freedom, 4,000. That's our sum of squares within the group, 796. Divided by 796, 494. Divide this into this, and it comes out to be 8.2. That apparently is big enough for us to reject our null hypothesis and say there's a difference in the mean for at least 2 of these groups, right? So let's see which ones they are. So we're going to go run our analysis of variance, compare means, one-way analysis of variance. This time I'm going to go into post hoc, check off Tukey, click continue, say OK. And again, this time we're going to get a bigger table because we have more variables to compare. Okay, so let's see what we have. I got one there. You can reject the null hypothesis that the mean of non-Hispanic whites is equal to non-Hispanic blacks. Say this just reiterates that. And you want to know something? Except for a close way, we also say Hispanics, the mean for Hispanics, mean weight for babies who were Hispanics in this population was different from the mean weight for non-Hispanic blacks in this population. I don't know what non-Hispanic was. I got non-Hispanic white. Okay, so at any rate, so we have that. We came close with other and non-Hispanic blacks. But you want to know something, we really probably would reject the null hypothesis there too. Every semester I get somebody asking me a question, what if it comes out to exactly 0.05, right? I mean, that 0.05 is an arbitrary number, so you'd probably reject the null hypothesis. Anybody here ever read Catch-22? No? Yeah, somebody read it, right? Somebody, who read that? You read that? Somebody said yes? Somebody. Yeah, you have read it. You remember what happened? It's about these American bomber pilots and crews that were in Italy during World War II, and they would have to go out on bombing missions. Except that it was very dangerous because there was a lot of anti-aircraft fire and so on and so forth. A lot of them get killed. In fact, if you look at the history of World War II, being in these bombers over Germany and Italy was very dangerous for these guys. So they would want to get out of the mission if they could. So the deal was if they were sick, they didn't have to go on the mission. So the policy was that if you had then this is the whole deal with Catch-22. Everybody's looking for an angle and it's nothing makes sense. So the deal was if you have a temperature over 102, you didn't have to go into the mission. You didn't have to go on the mission. If you had a temperature under 102, you had to go on the mission. So when they would go to the tent, if their temperature was 102, nobody knew what to do. So they would send them away, tell them to come back in a half hour so they can measure their temperature again. So, I mean, that's the same kind of thing. I mean, it's 0.05 is kind of arbitrary. So you could use it either way. So that's how we would do this analysis of variance. That's how we just do our initial analysis of variance. That's how we do our post hoc test. Let's take another couple of variables here. Okay, so let's say I wanted to determine, I have in here premature babies, right? Premature, well, what is that? Well, 0 is not premature. One was premature, and I have in here whether the mother smoked or not. Okay, mother smoked. 0 did smoke. It didn't smoke. Okay, so those are categorical variables, right? Mother smoked, yes or no? Mother had a premature baby, yes or no? What if I wanted to determine whether there's an association between a mother smoking and having a premature baby? What tests should I do? Categorical and categorical. Think last week. Chi-square, right? We want to do a chi-square test there because we're going to create a contingency table. Right in the rows is the smoking, yes or no. In the columns is the outcome. Was the baby premature or not premature? So I'm going to go to analyze. I'm going to go to, well, where's chi-square? Chi-square is under descriptive statistics, mostly because you start off by creating that crosstabs table, organizing the data. So in the rows, I'm going to put the whether the mother smoked during pregnancy, in other words, the exposure. And in the columns, I'm going to put the outcome, which is whether or not the baby was premature. Put that in there. And I'm going to go into cells, and I'm going to tell it I want to see the observed values. I want to see, let's see, percentages by rows. I'm going to click continue, and I'm going to want to go into statistics. I'm going to want to find out chi-square, and I'm going to want to find out risk ratios. I'm going to click OK. Okay, and I'm abbreviating this whole thing. If you go through the online session, the review session we had on Thursday, you'll see this explained a little bit more carefully. So what do I wind up with here? Okay, I wind up with, here's my chi-square table, right? Mothers who did not smoke, there were 684 mothers who did not smoke during pregnancy. 606 of them did not have a premature baby. 78 of them did. Well, 114 mothers did smoke. This data is from like the 80s or 70s or something like that. 114 of them did smoke. 15 had premature babies, 99 didn't. It's kind of hard to tell if there's a difference, right? Well, in fact, it doesn't look like there's a difference. The risk of having a premature baby was 88% of not having, oh, well, actually, this is the number that's the risk for having a premature baby. It's 11.4. For mothers who did smoke during pregnancy, it's 13.2. So what's our relative risk? It's 13.2 divided by 11.4, right? So what about chi-square? Can I say that my null hypothesis is that there's no association between smoking and the outcome of having a premature baby. So now I have to calculate my chi-square value. My chi-square value is 0.29. Now, with a 2x2 table, we know it's to be up around 3 or 4 or something like that. In fact, what's the probability we'd be wrong if we reject the null hypothesis? It's 0.589. So it's too low. I failed to reject my null hypothesis. There isn't enough evidence here for me to reject my null hypothesis that smoking is associated with premature baby. Maybe low birth weight. Let's take a look at low birth weight in a second. Now, as far as the risk is concerned, right, if I go down here, you'll see that I have another table that says a risk estimate, right? And remember I just mentioned the number, relative. See, here's the odds ratio, is 1.17. You're 1.17 times as likely to have a premature baby if you smoked versus if you didn't. But notice the confidence interval includes 1. Excuse me, I was about to say 0. You're right, 1. So again, that suggests you can't reject the null hypothesis. So that's how we would do that. Now I just brought up something else. What about smoking and whether or not you have a low birth weight baby? The birth weight is what kind of variable? Continuous, a numerical variable, right? And and low birth weight is yes or no, right? We have a variable that says low birth weight, yes or no. I think. Let me check. Low birth weight, yes. Low birth weight, 0 or 1, right? So we have a categorical variable, but we want to compare the means between those two categories. What test do I use? It's two means, right? So what do we use? T-test, right? Everybody, you guys starting to get this? The test, the data, the nature of the data, the type of variables they are, determine what test you use, right? So if you see I got to compare two means, it's got to be a t-test, right? So I'm going to compare two means. Analyze, compare means, independent samples t-test, right? Smoking mothers versus non-smoking mothers. And now I'm going to put my numerical variable in here, which is my weight, birth weight, weight of the baby in ounces, and my grouping variable, which is smoking status, in here. Now notice, remember what I told you? It comes up with 2 question marks because it wants me to tell it what those values are. And I think they were 1 and 2. Were they 1 and 2 or 0 and 1? Maybe 0. Maybe it's 0 and 1. What's that? Anybody remember? I'm going to say 0 and 1. If it doesn't work, I'll go back and change this. Click OK. And my t-test worked. My t-score, let's see. Independent samples t-test. Now remember, we decided we're going to stick with this bottom line. We're not going to worry about this test for quality. We're going to stick with this bottom line. My t-score is 3.84. And my significance is 0.000. Wow. It looks like I can reject my null. What was my null hypothesis? That the mean birth weight for mothers who smoked is different from the mean birth weight. Is the same as the mean birth weight for mothers who didn't smoke. The alternative hypothesis is that they're not the same. They're different. Okay? And if I look at the mean weights, well, for mothers who did not smoke, it's 117 ounces. For mothers who did smoke, it was 109. And that's apparently enough for us to, with very low chance of being wrong, to reject the null hypothesis. That's our t-test. What if I knew that in Europe, let's say this is going to average out to about 115. Let's say I knew in Europe that the average birth weight for babies in France, they keep data for every baby in France. The average birth weight for babies in France is 119 ounces. I know it's not ounces. 119 ounces, right, for argument's sake. And I wanted to compare babies in North Carolina to that. Well, now all of these babies qualify, smoking mothers, not whatever. I just want to compare the mean for all of them. And I want to compare that to the known mean for babies in France, which is 119. Well, what kind of test is that? Mean versus mean, that's a t-test. Except this time it's a single sample t-test. I'm working with a sample here against a known value. Analyze, compare means. Compare means. 1 sample t-test. I'm going to move in my weight for the baby. And I'm going to put for test value 119. The mean I'm comparing it to. In other words, mu is equal to 119, or mu is not equal to 119. And let's see what kind of result I get there. And my t-test, I'm going to get 1 row here because only a single sample. My t-test here says, yeah, look at that. That in fact, the mean for us is 116, the mean there is 119. So babies in France have a higher birth weight than babies in America based on that analysis. Okay, so so you got t-test, you got chi-square, you have odds ratio. What did I leave out?
Yeah. So if you have 2 means, it's a t-test.
Right.
If you have 2 categories, it's chi-square.
And odds ratio. If you have a 2x2 table, you can also do odds ratio or relative risk. If you have a 3x2 table. Let's say that you wanted to compare, let's say the smoking variable was mothers who smoked during pregnancy. Well, let me rephrase this. Mothers who did not smoke during pregnancy, mothers who smoked less than 1 pack a day in the pregnancy, or mothers who smoked more than 1 pack a day. So we have 3 rows and 2 columns. So now you can't do odds ratio because it's got to be a 2x2 table, right? You could create a new variable, which is just mothers who smoked and mothers who didn't smoke, right? 0 and 1 from 0, 1, and 2, right? You could go in there and create a new variable, so it's a 2x2 table if you really wanted to. But in that case, you would just do chi-square. Right?
What's that categorical variable called when you just have two